This is, I don't know, I got this down from some kind of show about science. You recognize any of these equations here? Right? If you said electrodynamics, a lot of this is from electrodynamics. This is supposed to be an illustration of what modern physics is. Equations, right? And then these people, the lab coats, are sitting around thinking about the equations, right? They're not really doing nature. They're not studying nature. They've just got these equations built up on the blocks. That's kind of an illustration of the equation alone physics. This brings the point home further. The equation alone physics. Okay, so there's some guys looking at the whiteboard with equations written on it. In the background, if you look carefully, hey, behind it, there's a tree and an eagle and a mountain, something else. Oh, there's some clouds, little bits of clouds. Nature's back there somewhere. But what's right in your face is the equations. Equations of physics. That's the way modern physics is understood by modern physicists and the way we teach it, for the most part. That's the way it's always done. This is the way it should be, the fully physical understanding. The equations are there, but they are, in fact, revealing to you things about nature. So you don't just look at the window and there's something written on the window. You look through the window into nature to understand nature better. In fact, the equations reveal to you more things about nature than you would have gotten without the equations. Well, you can see this displayed here as a magnification on the ladybug, where you see the rabbit up close, or some detail about the eagle. So nature is there, and the equations are aiding and helping you to understand nature better. The goal is nature to understand the world, not just to understand the equations. And to succeed at this, you have to be always working at it. It's not something that you can put aside. So you're going to learn the equations here. You're going to understand them in context, learn what they mean. It makes it more intelligible for you. In fact, nature helps you to understand the equations help you understand nature. So I think this is really good. This kind of set it up so you can switch back and forth. Oops, there we go. Contrast the two, right? So that's the goal of the physics for realists, is to go from the situation, which is currently the way virtually every course is, to that. That's the goal. It's not an add-on. This is not something that's kind of something that's not really very important. You just kind of add the stuff on. When are we going to get to the equations? That's not the point. The point is that, in fact, if you spend time understanding what you're doing, the physics will become much deeper for you. You'll understand it better, and you'll enjoy it more. It's much more enjoyable because it makes sense. Notice how I use that word. It makes sense, right? How do we begin? We begin with our senses. Okay, so chapter 1 is an introduction to the topic of the book. It wasn't that long ago that we started understanding that atoms, that massive bodies, massive substances are made up of really small parts. Obviously, we have parts. We have parts. Both of them are ones that you can feel, right? But you could use a microscope to look at things. So there are obviously smaller parts that are visible to the eye. The microscope is an important tool for you to understand the smaller parts. I'll get to that when we get there. Anyway, about 100 years ago, there was finally accumulating strong evidence. It took time for the technology, which was the fruit of the scientific revolution that was taking place, improving the technology. Because you understand the materials better, you can make use of them and make better instruments. So we were able to accumulate evidence about the existence of atoms And it was only about 100 years ago. It's not that long ago. If you think about it, it's not long. But be careful. You've never seen an atom. I can say that with a lot of confidence, right? I don't know anybody who has seen an atom. Dr. Padilla works in the laboratory, nanotechnology, nanofabrication laboratory. Have you ever seen an atom? Not directly. Not directly, no. You're looking at even if you put it under a microscope, shows up on the screen. There's an atom. Well, that's not an atom. That's an image on the screen made by this process of an electron beam going through the sample. If you don't understand the electron beam, how it works, you really don't understand the image that you're seeing. So you don't have personal, proper knowledge, scientific knowledge of atoms. You have heard about them. And you're relying on the authority of your teachers, most of whom have never seen an atom, right? I'm not saying that I have serious doubt about the existence of atoms. What I'm trying to get you to do is to be careful, talk about things you know well, and be very careful about things you don't know well. And so the first 2 semesters of this sequence, mechanics, electricity, and magnetism, are about things that you can have good experiences with. Now we're getting into a realm that's difficult for us, so we've got to be really careful. And he's very precise in the textbook. Read the textbook precisely because he's not jumping. He's going to walk you through this. And so one of the things that's really good about this book is that it starts off with experiments. And we're going to study the experiments. And so be careful about your conclusions from the experiments. He's very careful in describing the experiments. Don't bring in stuff from other places because it's confused. Don't go to Wikipedia especially. It's just confused. Stick with the book. It's really excellent. Okay, so unfortunately the demonstration didn't work, but we have a video made by one of my colleagues in the IT. So this is an image. Let's see if I can get it bigger. No. A little bigger.
It just click wash on you.
I'll probably get it bigger for me. Let's see. Yeah.
This is the checkers game
Oh,
with
I gotta
grandson
get the
and
commercial
granddad
first.
will talk. This is the
I want to mute this. That is muted at all. You have to mute it down here. Okay, so this is what I wanted you to see in the microscope yourself. And in the labs, you'll get to watch this. Oh, they rearranged it somehow. Okay, so these are polystyrene spheres in water. These are a micron diameter. How big is a micron?
1.
Go ahead.
Oh, that was a rhetorical. I'm sorry. 1 micrometer.
Micrometer. It's a micrometer. So a centimeter is about like that. 1,000th of a centimeter. 1,000 of those put end to end would be about that long, right? Small, but you can imagine using a microscope. They're not really small. So let's go back. No, I don't want that. Oh, stop. There we go. Okay, now this was something like this was what Brown noticed. I forgot exactly when the Brownian experiment was originally, probably 1800s. He was looking at pollen grains in water. He was studying the pollen grains and they kept moving around. And he thought, oh man, there must be something. Maybe there's something inside of them that's making them move around, doing something alive. So he took the pollen grains and he baked them to kill whatever was in there. And he put them back under the microscope and they're still doing this. Couldn't figure out what was going on. Why is it doing that? It was Einstein who figured it out in the early part of the last century, early 1900s, that this is evidence for the existence of atoms. That the water is bouncing this thing around. There's a lot of water molecules bouncing into the spheres or to the pollen grains. But there's only so many. And so every now and then there's more of them coming in from the one side than the other. So it bumps it off this way. And now there's more coming in from the bottom, so it bounces it this way. So it's doing this kind of jiggly motion. And in fact, from that analysis, Einstein was able to get a good estimate of Avogadro's number, the number of the density of the water molecules, how many water molecules per cubic centimeter, milliliter of water. So that was an outstanding advance. Really cool.
It's the most cited paper.
Is it really?
Yeah.
It's the most cited Einstein paper. Okay, this was part of his miraculous year. He had 3 famous papers, all written at the same time. Poor guy couldn't get a job when he got out of school, as brilliant as he was, partly because he wouldn't fit in with the German system of professors. He didn't like having to work within that system. He got a job as a patent clerk, not even in his home country. He had to go to Switzerland for this. But he says, in fact, it enabled him to do a lot of fundamental research that he wouldn't have been able to do had he been a professor at a university. In fact, the joke is that maybe he never would have gotten tenure. Yes, sir.
Einstein made all his big discoveries when he was like 60, right?
No. He was in his 20s, and he was working as a patent clerk. His what was called the miraculous year. He had 3 papers that he published simultaneously. One was Brownian motion. The other was his explanation of the photoelectric effect that we were talking about. So in many ways, he was one of the founding fathers of quantum mechanics. And the third was special relativity. He then went on to work more on quantum mechanics and general theory of relativity, which is the theory of gravity, in his 30s, I guess. So by the time these papers came out, he started getting to be known. But the job in the patent office was, he found it so easy. He was analyzing these patent applications. He found it easy to get it done, his work done in about a half an hour. He put stuff in the desk drawer. He started working on his special theory of relativity. And the supervisor would come by, "What are you doing?" "I finished my work. Here it is. Leave me alone." So he could get it done, and that freed him up to do this stuff. Miraculous. Fantastic year. So what he recognized was that there were a lot of so-called random, meaning we don't know the details of these collisions. And we're going to study this in terms, this introduces the concept of a random walker. So what is a random walker? You take a coin and flip it and determine it, whether you get heads or tails determines whether you take steps to the right or to the left. Flip another coin, flip another coin. That's just one walker who makes some number of steps. Okay, everybody in the room is going to get a coin, and everybody's going to do the same thing. And we're going to make a histogram of the final positions. Everybody starts at this place. How far to one way or the other do we end up? Each person will end up in some other place, right? We'll get some people, most people are going to be inside here. Some people are going to be way out in the tail to get a string of tails and end up way over here. Okay? So we're going to study that distribution. That's the Gaussian distribution, if you do it enough coin tosses. So we make a histogram of that. The width of this distribution scales like the number of coin tosses, the square root of the number of coin tosses. That's really interesting. That's as different, for example, than if I gave it a kick and I just wait for how long it goes, then the distance traveled is proportional to the time. Whereas in this case, it's proportional to the square root of the time. Yes, sir, Mr.
Campbell.
Campbell, thank you.
So the left side where it's at 0, 0, that's the people that ended up back in the same position.
Oh, no. This is the same position. I'm sorry, you're correct about this. The reason for this scale being offset, this is the starting place.
Oh, okay.
The reason for the scale being off is it has to do with the number of actual coin tosses.
Oh, okay.
And you'll see why it's, yeah, that is kind of confusing. I should just erase the axis on the bottom. That might help or re-increase. So this is an important thing to understand about atoms. We need to study atoms and not what we think about atoms, because what we think about atoms has been fed to us by people mostly who don't know. So this is an important aspect that Feynman made clear. When we were, he said, I have a terrible confusion between the symbols I use to represent things and the things themselves. recognizes he has this problem, doesn't quite know what to do about it. It bothers him. The symbols meaning the math. He understands the math at that level very well, but he's got a confusion between the symbols, the math, and the thing. And this is what we're trying to avoid. We want to understand that. Okay, so we need to be careful to study atoms and not just the mental constructs. So here's a fundamental puzzle about atoms. It's very interesting aspect. We learned in electrodynamics that a charge that's accelerated by some force will radiate energy. So when we were coming to understand the structure of the atom, we began to understand there were electrons going around a positive nucleus. The electron is accelerating, experiencing a force that's attracting it back to the nucleus to keep it from going away. Well, why doesn't that radiate? And if it radiates, why doesn't it just spiral in to the nucleus? The solar system, that's the eventual fate of the solar system. The planets are spiraling inward. Over enough time, they will just collapse. It will just collapse. It's going to take a long time. But the principle in the atom is why is the atom stable? Why doesn't the electron just collapse onto the proton, onto the nucleus? So this we will come to understand in the process of this. And the keys to this lie in the beginning of our understanding, lies in understanding at least some general way these experiments that were done in the early quantum days. So we're back to about 1900 up to about 1928 for these experiments. And it's important for you to understand them because I don't want to just start giving you equations. And then you think you understand the subject. Yeah, Mr. Campbell.
Is it possible that they are collapsing? It's just so slow that we can't perceive it? Is there some way that, I mean, because if it's so slow that we just can't detect it?
Sure, it's a possibility it has to be examined. And to
It
the,
would have to be a long time after. The universe has existed for 13.8 billion years.
well, we haven't been making measurements that long, but he's right about that. There have been obviously stable structures involving atoms. But to the best precision, and we can make these experiments to high precision. So we're talking about if there is an atom that's not stable and it's ground state, then it's really slow. I mean, really slow. So it's much slower than we would expect based on our understanding of charges. The rate of radiation should make them decay much faster than we see them.
We could also know how fast it should radiate by just firing an electron in the circle, right?
Yeah, that's right. That's true. Correct.
Say that again, I'm sorry. Confused.
You could just take an electron and fire it in a magnetic field, so it would go in a circle, right? And then you can experimentally see how fast it should radiate.
All right. Do you remember
So you're
that?
accelerating it to make yeah.
So you remember the cyclotron orbit and electromagnetism? You take a charged particle in a magnetic field, shoot it in, it'll go on a spiral.
Yeah.
And the radius of the spiral depends on how fast it's going. And that will radiate, and you'll see the decrease of the spiral over time, and that can be measured. And it agrees with the calculations that you could do. But when it gets to be this small, something else is coming into play. So these are the experiments that are discussed in the book. Black body radiation, take a heated piece of metal, make a little hole, look at the light coming out. The prediction based on just classical Maxwell's equations would say, and then we're going to analyze the light coming out in terms of its color, frequency of the light here. Just based on Maxwell's equations, you expect this to diverge. That is, the color should be way over to the right, high frequencies. But that's not the observation. Simple observation. There's something very different than what is expected. This is really simple to do, and the disagreement is very strong, it's very profound. So that's discussed in the book. I'll leave that. You need to read what's in the.
Can you go back to the chart really quick? The
Yeah.
graph.
Right there.
Thank you.
This is in the book.
So when we say radiate, what are we talking about? What's something?
You remember the chapter on radiation?
Yes, sir.
That's what I'm talking about. Electromagnetic radiation. It emits electromagnetic waves. And so the energy of the particle is diminished because the electromagnetic waves are carrying analogically energy.
So it loses, oh,
It spirals in, it loses energy.
so does that mean something's acting against it?
Yes. Hold
That's
on,
not-
hold on. Don't make a conclusion yet. We'll get there, but that's part of the discussion. But we're trying to uncover why. Okay, then, so the description of this black body radiation involved a guess by Planck in the late 1800s. It's not what most people think. It's not the quantization of light. You'll hear this. That's not correct. The conclusion that be made from this is that energy can be emitted from the atoms in the wall only in bursts. That's not to say that light is quantized. It has something more to do with the process of emission in bursts. That's the conclusion from this. That's his guess. He's guessing this. And he's able then, based on that guess, to get exactly the observed spectrum. He doesn't understand what he's doing. He's openly saying, I don't know what this means. But if I do this, I get this answer. It's an example of the empiriometric giving something we don't fully understand, right? It takes time to digest. But it's very helpful. It gives a very important bit of evidence that we need to discuss. So, according to the Newtonian dynamics that you studied in mechanics, you can change the energy of systems continuously. There's no discreteness in the energy of a system. But Planck is saying somehow that energy can be emitted only in lumps, very small lumps, but only in lumps. That's a radical idea. So he goes through this in the book to study this, the result that you get, the spectrum, energy spectrum. Okay. So I'm going to leave that for what's in the book for now. The second one is very important. Again, something that Einstein contributed to was the understanding of the photoelectric effect. And again, Planck was involved in this experiment. Planck was involved in an experiment. We take a piece of metal, shine light on the metal, and then look for electrons coming off. Again, they're discovering electrons, for example. How this is one way of producing electrons. So you have a setup with an electrode where light is shining on the electrode. You're going to have a demonstration in class about this, and you'll also do it in the lab. You'll do that same experiment, the photoelectric effect. And Einstein says, again, this seems to be evidence for light interacting with the metal and transmitting energy into the metal again in lumps, which you wouldn't normally expect, not from Maxwell's understanding of electrodynamics. You have an electric field that's oscillating, you have a charge that's got a force on it, and so you should just be able to increase the intensity of the light, and that will give the electron enough energy to pull it out from the solid that is in the metal. Doesn't work that way. Doesn't matter how intense you make the light. The important thing is the frequency of the light. So if you go towards ultraviolet light, then you get electrons coming off. But if you use color that's below some threshold, nothing comes off. And in fact, once you start getting a threshold, once you start getting electrons out, if you can increase the frequency of the light, electrons are coming out with more and more energy as you increase the frequency. Very strange effect. And this was what got Einstein the Nobel Prize, not relativity. Okay, so here's an example. There's no current coming off. Actually, it's measuring kinetic energy, electrons coming off. Nothing's coming off until you reach a certain threshold. After that, if you increase the frequency, then the energy of the electrons coming off is increasing. This is irrespective of the intensity of the light. You can turn it on, make it 10 times brighter. If you're down here, you're getting nothing coming out. So it's not the intensity of the light, not the strength of the electric field. Something strange going on. Okay, you'll see in many textbooks, also on Wikipedia, various places, people will say that the photoelectric effect demonstrates that light is quantized. that it comes in photons. That's not correct. I'll show you the experiment that does demonstrate quantization of light, not the photoelectric effect. The photoelectric effect shows you instead that there's a threshold. Electrons are down here at some energy, and they can't get out, and they have to climb some hill to get out of the metal, and the light has to provide that energy. This is evidence that the electronic states are quantized, not the light, but the electron states. You can understand almost all of the photoelectric effect measurements by that. Just not quantization of light, but just the quantization of the electron states inside the metal. We'll talk more about that. Okay. So after he published this paper and he wrote some other papers that didn't get published, that he did not publish, I should say it that way. He was unhappy with it. He stuck them in the drawer. But he had his own quantum theory 20 years before anybody else did. Not quite right. More than 10 years. And he kept talking to people and saying, quantum mechanics, something is going on here. We need to study this. We need more experiments. And he felt like he was a stranger because there weren't very many people who were interested. That's strange. He knew there was something going on in quantum mechanics, something going on in atoms and things related to that. But he couldn't convince people to work on it. Kind of strange. Another experiment done about this time was the Frank-Hertz experiment. And you'll see the setup here is you have two electrodes. And again, they were able to start getting electrons to come off by applying a voltage that's high enough. You can strip electrons off from a heated element here. And then electrons are channeling through this region here, which then if you fill with a gas, you get a glow. This is like a neon light operates in this way. Okay, so let's see. So this was a video, this is a setup of another colleague of mine, Stanford University of Birmingham. And he's got this setup just like I showed you. And then he has to turn off the lights and you can turn on the current, turn on the voltage, and watch what happens inside. It's a little dark. Let's see if it got me better. He sent me a better version. There it is. The glow of the gas, and then it goes away. He's increased the, oh, there's a little bit more. Okay, something's happening. Again, there's a threshold. There's a threshold voltage. Nothing seems to happen. The electrons are going through, but they're not exciting the gas. They don't have enough energy to excite the gas. And then it's like it goes away and then comes back again as you keep increasing the voltage. Something weird is going on. Here's another, this is a video where it's a little hard to see. He's measuring the current. So how much current is flowing through the cell? He's increasing the voltage. And look, the current went up and back down. Now the current's going up again, back down again. And you can make correspondence of these peaks with the light coming out of the cell. 3 peaks, 4 peaks. It keeps going. Strange. What's going on with this? Why is there 1 peak at all? Much less why are there 4 peaks? Something is going on there. Again, it's an example of some kind of quantization. Something is happening where the energy has to be just right to match up to cause the excitation in the atoms. But there's too much and it goes away. But then there's the second peak. So here's the figure it's in the book. Strange. The real proof for the quantization of light did not come until like 1926. The Compton scattering experiment, where Compton, I guess this was this in California? Did this experiment? I'm trying to remember where Compton was. Anyway, an American scientist who scattered light off an electron. In this case, the electrons were in the atom, and he was able to analyze the energy of the light after the scattering was consistent with light being a particle, not just a wave. This is really strange. This is finally the jarred people's thinking about quantization of light. We're not going to study this anymore. this is the end of that. We're going to study the quantization of the atom. We're going to study the quantization, the quantum mechanics of massive bodies and the parts, the electrons, protons, parts. This is a different subject. This is quantum field theory. It's the quantization of the electromagnetic field, which is a very difficult subject. Takes a lot of time for you to get prepped in it. Dr. Rizzi's working on a book on quantum field theory. Yes, sir. Mr. Silva.
Yes. Sorry to make you repeat yourself, but so we're not gonna be doing wave particle duality in this course.
No, we are, because people talk about wave particle duality for the electron. We are not going to be studying the quantization of the electromagnetic field. The name of the theory that Feynman invented was quantum electrodynamics. And that's what he got the Nobel Prize for, along with others, Singer and Tominaga. We're not studying. That's a mathematically difficult subject. But we're going to start the beginning of the study of quantum mechanics with studying the quantum nature of massive bodies, not the light, but the massive bodies themselves. And historically, that's the way it came out too. Okay, so the constant scattering shows we can associate an energy with the light, which is proportional to the frequency of the light, with that proportionality constant, which had been measured in the photoelectric effect. This is called Planck's constant, and it's proportionality between the energy and the frequency. Also, the light seems to have momentum, which is proportional to the energy. The proportionality is the speed of light. And so we're going to study these two relations, lay the groundwork for chapter 2. These two relations are going to be our guide in coming to understand what's going on, to the extent that there is a similar relationship for the electron as well, a relationship between the energy and the momentum, and a frequency associated with the electron. Yes, sir.
You mind going back one slide?
That's sure. Oops. Yes. We're going to talk. I have some other stuff written here. There's a K, which is called wave number. We'll talk about wave number. It's coming. The important thing here is the relationship between the energy and the frequency for light. There's also a similar relationship between energy and the frequency of an electron. What is that? Frequency of an electron. That's okay. And also, we're going to talk about the relationship between the momentum and the energy. And there's another thing that comes in relation to that is the wave. So that's coming. It's just laying the foundation. The constant scattering starts to give us some empiriometric beginnings, some quantitative relationships between things that we can start writing formulas about. Okay. Another one is the fact that light emitted by hot hydrogen atoms or light absorbed in hydrogen. So in this case, you're seeing the emission. In this case, it's an absorption. So light is passing through hydrogen, and the hydrogen is pulling out. It's absorbing light. It's not letting it pass if it has certain frequencies, and the frequencies correspond to the emission lines as well. The absorption and emission lines line up. Two different things going on. What's going on here? The surprise isn't that hydrogen absorbs energy from electromagnetic waves. The surprise is that it only happens at certain frequencies. What are those frequencies? And as you will see when we get to it, this was the thing that Schrodinger matched to when he developed the theory of the hydrogen atom, which you will learn. He was able to explain this series of colors. And when he did that, he knew he was onto something. Here's another really interesting one. So suppose I have an electron beam, and I'm going to, this has to be done in vacuum. And I'm going to scatter the beam off of a nickel piece of metal. And look over here, I put a screen over here, let the electrons strike the screen after they scattered off of the nickel, they bounced off the nickel. That's what it looks like. This discrete peaks called a diffraction pattern, and we'll study what diffraction means. the electrons are diffracting off of the crystal structure of the nickel. Very strange. That's totally surprising that this should happen. This was actually predicted before it was observed by Louis de Broglie, who made a prediction about the diffraction of electrons. Totally surprising, though. If you think of electrons as being simply a particle that bounces off of things, it should not show up as a diffracted pattern like this. Very strange. Okay, so Davison and Germer did this experiment again after the predictions had been made. Yeah.
Just to clarify on the picture, each bright dot is several electrons.
Yeah, let me explain that because that's an important point. Thank you. Okay, this is what happens if you turn the beam intensity is you've got lots of electrons coming out. You see this pattern on the screen. Here's something really strange. I'm going to turn the current down on the beam. So I get just one electron. That would be ideally one electron at a time. And then look for where it shows up on the screen. Now you see only a spot here, and a spot there, and a spot there, and a spot there. Each electron is showing up just one place on the screen. It's not until you accumulate all of the incidents, all of the spots that occur, accumulate them over time, that it looks like this. Strange. Each electron shows up as one little blip somewhere on the screen. And in fact, you will see there are no electrons ever showing up in these dark regions. They're only showing up, they'll show up here or here or here, somewhere inside of a spot. But each electron is just one little blip. It's not until you accumulate a whole bunch of electrons that it shows up like this. Very strange. Yeah, Mr. Silva.
Does it represent Gaussian distribution, or is that like trying to connect?
It's not a Gaussian, no. Yeah, it's a good guess. Why not? Let's take a cross section of the intensity across here. It's not Gaussian.
Yeah, it's like Gaussian that have continuous distribution, right?
It is a continuous distribution, but it's not Gaussian.
So I was talking about Gaussian distribution is continuous.
Yeah,
And
this is continuous, but it's not Gaussian.
wait, that's continuous?
Sure.
There seems to be Gaussian.
I said, take a cross section across the spot here. If you do a cross section, you could analyze the intensity. So this is the intensity across the spot. So this is one of those spots. Okay, that one. Go across it, measure the intensity. It's continuous.
Oh, I thought that meant there was no electrons there.
No, the no electrons are in between the dark region.
That's what I was
So out
talking
in the tails. Out in the tails, there's no, right? This is you get where there's a peak, you get a lot of electrons. In between, you get none or very, very small number. But it's not a Gaussian distribution. And in fact, the distribution tells you a lot about the structure of nickel, by the way. So we're going to be studying diffraction. And so it's helpful just to have some familiarity with diffraction. So here, you could do these sorts of experiments in the bathtub. Right? So here we have some water waves coming through. We have obstacles. The waves would ordinarily just roll by, but these obstacles do something. And then what you see, the result is that the obstruction has caused some kind of pattern change in the waves in between. This is called diffraction. So, in fact, what happens with the diffraction depends on, there's two factors. The waves have a distance crest to crest. It's called the wavelength, right? So the water waves, they're traveling, say, this way. This distance we call the wavelength. So this is the distance between crests. How big is the opening in comparison to that wavelength? This will determine how much diffraction you get. The smaller the opening as it approaches the wavelength, it's going to cause more diffraction. If you have a bigger opening, much bigger than the distance of the wavelength, you get less and less of a diffraction. It doesn't look to be distorting the wave as much for it to go through. So that's the critical ratio, is the size of the slit, the gap, to the wavelength. So we're going to study this. Here's an interesting variation. Got waves coming in, we got two slits. Double slit interference pattern. And now look at all this out here. So you've got three lengths now, the wavelength, the slit width, and the distance between the slits. A lot of interesting things can be done to study this double slit pattern, this interference pattern. Yeah.
I just want to make sure that the distance, the distance of the slits, you said it has to be, it has to be like near the same length as the wavelength.
No, I said that this gap has to be on the order of the wavelength, maybe 2 or 3 times that shorter. To get diffraction, you need this gap to be small compared to a wavelength. That's when you get really a lot of diffraction.
Oh, so if you want a lot of diffraction, you make that gap small, a lot
Yeah.
smaller than that.
Less light through or less wave goes through, but it produces more diffraction of what does go through.
Okay, awesome.
This is a variation on the theme. Let's take 2 slits. So we have also the distance between the slits. And it produces a really interesting pattern here on the far side. This is what we're going to study a lot, this double interference pattern, this double slit interference. Okay, so if you do it with waves, just ordinary waves like water waves, or laser light, we're going to do it with laser here in the classroom. With the double slit pattern, you get fringes, interference fringes on the far side. That you get maxima and the light separated by distances. So the interference pattern on the screen will be very complex like this. It's kind of envelope. So there's a width to the interference pattern, this overall width, but there's also peaks inside that have width to them. And there's zeros. That is, there's no light showing up here. I haven't succeeded in doing this in the bathtub, but you should be able to do it. It's got to be quiet, though. You can't be messing around with the water. You just got to, Okay. So here's the really weird experiment, and this relates to the double slit experiment with electrons. Diffraction with the electrons off of a particle. It's the same sort of thing. We've got electrons coming through, but okay, so we've got slits with some width, and then the distance between the slits. What wavelength do we use for electrons? There is a wavelength, as we will come to understand, associated with electrons. Kind of strange. And the wavelength depends on the energy of the electrons. Don't understand that yet, but we'll get there. But here's an observation. Let's have this electron gun. Somehow we make these slits to be the right size and the right distance apart. We shoot one electron through at a time. The electron shows a blip, one blip on the screen. It's not spread out. The electron's a particle. Shoot another electron. There's another blip over here. Another one, there's another blip. You accumulate all the blips or just turn the electron gun, so it's a whole bunch of electrons going all at the same time. And that's the pattern you get on the screen. You see this, but this pattern comes about one electron at a time. It's really strange. So this is an illustration. You get individual blips. If you record where you see them on the screen, you keep recording, and over time you accumulate enough blips, you see the pattern showing up. But only one blip at a time. That's really strange. What's going on there? That's quantum mechanics. Okay, there's some other things. The heat capacity of silver, heat capacity, I've got another minute. Heat capacity is how much heat does it take to raise the lump of silver by 1 degree Kelvin. You study heat capacity, I think, when you study thermodynamics last semester. When you make things really cold, the heat capacity drops off. This is really hard to understand from just thinking of the solid as made of atoms that are just moving around and bouncing into each other and connected to each other. Something is going on here. At low temperatures, the heat capacity is going way down, which means it only takes a little bit of heat to make the temperature go up really fast. Very strange. You're going to see some videos I've added. They're on Canvas. superfluids and superconductors. These are quantum experiments. Notice that most of what I've been talking about, I mean, they involve atoms and electrons in some cases, but the superfluids, these are macroscopic objects. You hear sometimes that quantum mechanics only applies to really small things. It's not true. And also you hear that it can only happen at low temperatures. Well, superfluids is an example of something that's low temperature, but it's not true that it only happens at low temperatures. But it is true from these early day experiments. A lot of them were done on small things at low temperature and so forth. Okay, so that's some of your reading. You should have read that today. And we're going to start analyzing this. This is for your homework for Monday. What does all this mean? We're not going to jump. We're going to walk slowly. And we're not going to start pulling in strange contradictions, try to explain stuff, because contradictions themselves don't mean anything, right? Remember, this sentence is false means nothing. So when you hear stuff about wave particle duality, really be careful there, because you might be bringing in a contradiction. We got to understand what's going on. We got to do it slowly. So I don't want you jumping off the Wikipedia or Googling stuff. Just stick with the textbook. Later on, after you understand what is going on, then maybe you can explore other things, because you'll be having some understanding of what's going on. If you try jumping into the popular press now, get an understanding of this, you will be totally confused by Monday. Right? Don't do that. Stick with the book. Okay, so we'll see you on Monday.